if there's any like delay or anything like that, I apologize. Let me just F5 over here, see if it's still online. Okay. Basically, I accidentally showed my my dashboard, and I didn't want everyone to see that. There wasn't anything on there that was particularly bad. I just don't like people seeing it. It's like proprietary, confidential information. It's not proprietary. Okay, so I was talking about Primer, YouTube. I'm gonna be honest. When this guy initially made like his first video, like a long time ago, he had no subscribers. He was kind of worried about not having any subscribers. I literally sent him a message, and I was like, "Yo, dog, I want to make a video with you. This guy's amazing. I genuinely like his stuff. YouTube channel. This must be it. No, that's not it at all. Let's do Primer. Here. There it is. That's what I'm looking for. And now he's got so many. I mean, he's just doing so well. I mean, he's wonderful. I can't believe he nabbed that username. To be fair, I don't really know what his username was before. I don't know. Like, I think that's just the public name he goes by. I don't know what his private name is. His private name is apparently UCKZJFDI. You know, whatever. I don't know. But what I wanted to say was that this guy's amazing. His visualizations are wonderful. He's honestly like, he is to me 3 blue 1 brown quality, and he's really, really, really good. I'm such a big fan of his stuff. And I wanted to do a video with him because I knew he was going to grow. And now look at him. He's at 268,000 subscribers. I'm now a small little chump change, small fry. You know what I mean? Like, it's okay. It's okay. I know that my channel grows slowly because I don't focus on video content, and I get that. Which is why I wanted to talk to you guys about this. So basically, we have a small, it's not a subreddit, it's a Slack channel, where we have a whole bunch of educational YouTubers all kind of talking about things. And I recently proposed something. I recently said, hey, guys, if, let's say I, as a researcher, came up to you as a YouTube content creator, and I really wanted to push my content onto your channel. That is to say, I'm a researcher, and I want you to talk about my research on your channel. How would this happen? And so I asked them, would this be considered a collaboration because the researcher is providing a lot of the content, or would it be considered a sponsored video because, you know, you are asking for monetary compensation for the fact that, you know, you're showing their content on your channel. Does that make sense? There's 2 different ways to go about it. One, the educational content creator could be saying, hey, look, I love your research, but I'm not going to make a video on it without money. On the other hand, the educational content creator could say, hey, look, I love your research. It's going to make a great video. Let's go ahead and make a video on that. You know what I mean? And depending on how this is received, it would be better or worse for the researcher. Does that make sense? So the question is, how do we get modern research to be shown on YouTube? How do we get it to be shown on Twitch? How do we get it to be shown at all so people can see it? And that's really hard to do. Because for the most part, YouTubers, and of course I'm only speaking for the few people who spoke in this small thread, for the most part, YouTubers would prefer a sponsorship by like Audible or something like that, because then they get creative freedom, like complete creative freedom. If Audible sponsors a video, they just have to plug it at the end. Meanwhile, if, you know, the Oyster Graduate School sponsors your video, it's gonna be kind of hard because now they want specific content in that video. And you don't have complete creative freedom. Sure, you have editorial freedom. You can say whatever the heck you want, but it should be kind of biased towards this guy's research in some ways. Well, not biased, but it should at least discuss that research. You know what I mean? Pretty sure the animation software he made is based on Madam. No, it's completely different. The animation software he made, it could be based on Madam. Okay, you're right. But it's certainly not Madam. It is actually done via Blender, which is really cool. Educational. So you're getting really great teachers to communicate your cutting edge research. That's what I was trying to do. You know, I was trying to link the researchers who desperately want their research to be shown to a wider audience with YouTubers who are oftentimes struggling to find new content, you know? So I figured this would be a match made in heaven. It's like, hey, here's some researchers who really genuinely want to talk about their research. But I don't know, for some reason, it didn't stick on either community, right? Because the YouTubers over here, they're thinking to themselves, well, look, why would I make a video on some other person's work? That seemed kind of weird. And then the researchers are thinking, well, why am I making a YouTube video when I could be publishing this in like, some sort of Nature press release or something like that, But the thing is, there is a small community, I think, of researchers who are now understanding that just doing basic press releases is not enough. That's not where people are. People are, whether you like it or not, on YouTube. You can find them on YouTube. And so if you're looking for people who care about and want to learn about your research, you can find them there. Now the issue is, and I've said this before, there are very few good examples of researcher YouTube channels. Let me just do Joel Carpenter. I love this guy. I mean, not in like a romantic sense. I like his YouTube channel. He's got my favorite researcher's YouTube channel. Like, of all the researchers I found, he has the best channel, in my opinion. Because he literally just posts videos, of his presentations, and of just random things for general audiences, and he's nice. I'm a big fan of this guy. Plus, he has one of the best YouTube videos I've ever seen for advertising PhD positions. It's literally just, one second, you'll see it in a second. It's just epic music in the background to fire saying PhD positions are available. That's all it is. This is the best advertisement I've ever seen for a PhD position. It's wonderful. I would love to be able to do something like this before. I think what you would need is 2-minute papers, but they use your papers. The only one I saw was a PhD video. I'm gonna be honest. As far as 2-minute papers is concerned, he's again one of my favorite YouTubers. I love the guy. Why do I keep saying I love people when I don't? You know what I mean. He's a wonderful person. I like his content. I think it's quite good. This thing has 3 likes, 61 views. I don't know why I like this so much. It's just every time I watch it, I laugh, and I find it's just so good. It's just so good. Anyway, my point is, as far as getting research to be presented on YouTube, I do really feel like this is some sort of niche that needs to be filled, because right now it's not being filled. And I would love to be the one leading that charge. You know what I mean? Sure, my videos have never been 3 Blue 1 Brown or primer level quality. You know what I mean? I think they're good videos, but I think in the end, the videos themselves are not anything to write home about. And I know that, I understand that, which is why, I have the algorithm archive and, this Twitch community and stuff like that. But I think one thing that I can do that other people can't is talk about the research that I've been doing, and it's something that I do want to move forward with in the future. It's just, I don't know. I don't know what you guys think about it. I know I've been kind of harping on it a lot. Why is that not erasing? I know I've been harping on it a lot, but I do genuinely feel like this is a good future direction to go in, because it's just not being done. Let me go ahead and pop over here. I realized I'm on the wrong screen. Oh, also, I'm just out of it today. I'm not tired. I'm just out of it. Like those days when you're fully cognizant of the world around you. You're aware of everything that's happening. It's just, for some reason, it's not happening as quickly as you want it to happen. That's today for me. Okay. So, as far as this is concerned, I figure let's go ahead and talk about some research that I did a long time ago. And that's working with the Daemon simulation code. So, one second. The Daemon simulation code. Now, Daemon simulation code stands for Dynamic Exploration of, we'll put an of here, microparticle, clouds, optimized numerically. Okay, I didn't come up with this name. Someone else came up with this name. It is a Dusty Plasma simulator. Dusty Plasma. Now, I don't think I've really spoken about my old school plasma research that I've done before going to Oyster. I really didn't do it much because it's not something that really came up, By the time you guys met me, I was already, a few years into my PhD program here, doing, quantum research. And this is drastically different. It's just that when I was making my previous video, I kind of realized that, hey, if I'm going to make videos on my research, I should really make videos on all of my research, including the research I did as an undergraduate. And now, admittedly, that research isn't nearly as good as the research I'm doing now, but that's okay. Because I think just having some sort of research to be done as an undergraduate is a really, really good step forward. I don't know if I said hey to you, Folster. Hey, how are you? So anyway, that's kind of my point here. I feel like we just need to do a better job of just talking about research and making it more common for people to hear about the scientific process and just hear about, modern research being done on, the social media that they're on. Does that make sense? Like, I feel like we need to talk about this stuff. And I myself, even though I say I want to do better at this, have not been doing better at this. So, dusty plasmas. Journal, new page before. What do you guys know about plasmas? I feel like at this point, it probably isn't too much. Let me go ahead and get some water. If anyone wants to answer that question while I'm getting some water and kind of just rambling a bit, feel free to do so. I guess I should ask, not what do you guys know about plasmas, because that's an open-ended question. I should ask like a yes/no question. Do you guys feel you have an adequate understanding of what a plasma is? Okay, C252 says he knows nothing. It's like really hot, right? Yeah, so I'm gonna be honest. This is gonna be a very kind of hand-wavy discussion of what a plasma is. So we have an atom, and I'm gonna draw this in a very crappy way. So here's our nucleus, which is again filled with protons and neutrons, and then on the outside we have these electrons, which I'm gonna draw in. Let's make them pink. All right. So we have these electrons in kind of an orbit on the outside of this atom. So we have 2 here, then I think we have 6 on the next one. 4, 5, 6, something like that. Forgive me, that wasn't quite an appropriate orbit. And then on top of that we have, more orbits and more orbits on the outside. Does that make sense? So obviously we have, a nucleus in the center, and then we just have a whole bunch of these electron clouds. If we basically heat up this particle significantly hot, the electrons on the outer orbits here become thermoionized. And now there's other ways to do this. It doesn't have to be specifically with thermoionized, but the point is they become ionized. This is to say the electrons start whirring off the atom. They start just flying off the atom, right? And if you've got a whole bunch of these atoms all together in some sort of gas, right? And you have all these electrons that are just like flying off the atoms left and right, well, you get this kind of weird atomic goop where you have the electrons just kind of all in this weird quantum-y state, some sort of weird wave, with these ions that are now just kind of floating in the substance. So now it turns into something that looks like this, right? So after everything's ionized, after all these electrons go flying off the atom, then we have this kind of weird pinkish goop, which is all the electrons, right? And then you have these ions, which I'm going to color in dark blue to signify that it's not just a nucleus, it's a nucleus plus other things, just kind of floating around in space, right? So that's kind of what we have here. We have a whole bunch of negatively charged electrons just kind of all floating in this weird goopy type of thing. And then we have these ionized particles, which are positively charged now because they're losing an electron, just kind of all floating around. So this kind of interplay between the negatively charged free electron gas, and then the positively charged ions, that's kind of what a plasma is. And again, I'm being very hand-wavy here because it's been like 5 years since I actually looked into what plasmas were and stuff like this. Like, it's been a long time since I did this type of research. And even when I did that type of research, I was an undergraduate, right? Like, it's not like I had a perfect understanding of what it was that I was doing. I was kind of more or less just doing what I thought I had to do, you know? So let me talk now about what a dusty plasma is. So let's go down here. Let's imagine we have this goop, right? So here's our goop box. Just everything in here is filled with some sort of electrons, electronic weird wave, free electron gas type of thing. Bohr model of atomic physics. Hey, Trash Talk, by the way, is like really hot. Yeah, basically. So here's our goop. And then on top of this, we have these ions, which are all over the place. Now, I know it's hard to see, but just forgive me here. There's going to be a much larger particle that I put in there in just a second. So we have all of these ions that are just kind of filling up this electron goop. Remember, this is positively charged. This is negatively charged, right? Now what we do is we put a big neutral blob right in the center, okay? This thing doesn't have positive or negative charge, but it's really, really, really sticky, which basically means anything that runs into the blob gets stuck to this blob, right? Well, okay, we have a lot more of these negatively charged particles, right? Because this is just some sort of giant goop. Then we have these positively charged particles. So we're going to have more of these. So that means more of the negatively charged particles are going to stick to this giant neutral blob that we have in the middle of the plasma, making it so now it's this incredibly negatively charged thing, because we have thousands of electrons for every one ion that sticks to this particle, right? Is it like an atom with lots of neutrons? No, usually it's like, it is a large, somewhat macroscopic object that you can see, right? It's usually like maybe some sort of compound, like some sort of maybe like silica particle or something like that. It's something that you're actually like throwing into the system to perturb the system. Like you're throwing it in to make it so that the system is, I don't know how to put it, but it's it notices, right? So it gets static charge. Yeah, basically like that, right? So now this particle here, which was originally neutral, now is usually about negative 1,000 electrons in charge. Does that make sense? So basically what ends up happening is, I don't speak Russian, sorry about that, Nikolay. This now once neutral particle has attracted a whole bunch more negatively charged electrons and positively charged ions. So it's now roughly, 1,000 electrons in charge, which is of course negative. And so this is kind of the heart of the dusty plasma. You have a whole bunch of these varying sized blobs that are all kind of sitting in the plasma. And they all act in kind of weird ways. And there's a whole bunch of weird ways that they work, right? Because now you've got this kind of weird model where these are now point charges. All of these blobs are point charges, right? Where they're all basically the same charge and they're all kind of basically moving in the same way. But now you've got this kind of weird case where you can actually see like what you'd want to see in like physics class or when you took electricity, magnetism, and physics, you always had that one question that was like, if you have two negatively charged particles distanced, so far away from each other, how do they respond, right? And you know that they move away because negative or like charges repel and opposite charges attract, right? But what's weird about this is that we have a lot of these negatively charged particles all kind of put into the same box, right? So now this is a perfect simulation for simple molecular dynamics. Oh, hello there. Let me try writing this correctly. Dynamics. Where we basically treat each of these guys as their own particles and they all kind of work together. Like there's some sort of force that is pushing all these particles around. Does that make sense, right? So like this particle here, let's say, this particle here feels a force from this guy, this guy, this guy, and obviously this guy back here, right? And it's true for all of these particles, right? They're all kind of interacting with each other so that they all feel forces from one another, right? So if you're going to simulate this system, you kind of have all of these weird negatively charged particles that are just acting with each other, right? And you can treat this as a molecular dynamics simulation, and you can actually ignore the underlying plasma and ignore basically all the other effects because the dusty particles are themselves so much larger than everything else in the system that you really just don't have to worry about it, right? You just have to believe in that each of these dusty particles are negatively charged and have the same negative charge, and then as long as that's the case, you can treat them all as separate objects. And do the same thing we did earlier with the galaxy simulation. Just instead of gravity, it's the electric force, right? So it's one second. Each force is going to be let's see, journal, new page before. Force electric is going to be equal to Q E plus V cross B, something like this. Where E is the electric field, B is the magnetic field. And this is the particle's charge, and that's its velocity, right? So the idea is we have this particle, it's moving around this weird type of plasma goop. It's got some sort of velocity. There could be some sort of magnetic field underneath. And basically, we have some sort of charge associated with the particle and the electric field from all the other particles and stuff like that, right? So each particle is feeling a force. That force, rather than being a gravitational force, is an electromagnetic force, and we just treat them all as individual particles. And that's kind of the whole simulation. It's not particularly complicated. You can probably see why now it was an easy undergraduate research project, because really we're just treating each of these particles as a separate object and we don't have to worry about the actual plasma dynamics and stuff like that. Now, to be clear, the area of dusty plasmas is incredibly important, but not usually important so that we can understand like how these particles interact. It's usually important because when you're doing a plasma experiment, right? Let's say you're doing a tokamak, which is a way in which people are trying to generate energy from plasmas right now, right? Let's say you have some sort of large plasma object that you're trying to get energy out of. Well, it turns out that humans are really, really bad at making clean systems, right? So every once and again, you're going to get these dust grains that are just thrown into your plasma, right? And you have to kind of figure out how these dust grains are going to act, why they're going to act in that way, what happens if there's a lot of dust in the system, all this kind of stuff, right? And more than likely, this dust is just automatically vaporized, right? Because the plasma is so hot. But there are plenty of places where that's not the case, and you have to kind of deal with these dust grains as if they were these kind of globs of charge that are just moving around the plasma. And so there's reason to do this research, but we were kind of attacking it from a different angle. Like, hey, how could we use these dust grains as a useful, engineering tool for the plasma, rather than the other way that most people use them, as seeing dust as this inherently bad thing in the plasma. We were like, hey, how could we use it for something good? And that's kind of what I was looking into. Now, the lab that I worked with before, I guess I'm going to go ahead and plug their name. The lab I was working with before was with Edward Thomas. Let me just go ahead and do this. So you can take a look at his publication record. I've obviously Googled him before. He's doing very well for himself, I think. He's at Auburn University. Here he is looking at his, this must be MDPX, or not MDPX, this has to be one of their old school experiments. But basically, he is doing the first, what is this? First experiments. Anyway, that's because I see. So he's like one of the leading experts in dusty plasma physics. He's really cool. Just really, really cool. I don't think I've ever met a researcher I wouldn't say is cool. And maybe I have. Okay, I definitely have, but you know what I mean. He's a really cool guy. This research was definitely fundamental in shaping my ideology towards research now, where I kind of do everything in a computational way. And I do genuinely feel that he was the one that got me into research to begin with. And so I'm very kind of indebted to him, I guess, for that reason. He was the first person to run the magnetized dusty plasma experiments, MDPX, which basically involves putting a magnetic field into these dusty systems. Now, here's the weird thing, right? So if you have this glob of negative charge, which I'm just going to notate like this. Let me try doing that again. Here, it's just a glob with a negative in the middle. And you put a magnetic field that's kind of going up in this direction, right? What's going to end up happening is this negatively charged particle is going to start to rotate about its axis. Something like this, right? And the reason it does this is because of something known as gyro motion or something like that. There's a good number of reasons why this happens, but basically it starts to spin, right? Now, with electronic systems, it actually has this thing called gyro motion where it actually rotates around in a circle, right? But if you have these very large, negatively charged particles, well, then it's just going to spin around on its axis, right? So the question was, if we put a very large magnetic field into a dusty plasma, how do the particles interact? And so this is a very interesting question, because it's an n-body simulation with the molecular dynamics simulation that now has this additional magnetic field term. And that was where most of my research went into at the time, asking how does this magnetic field term influence the dynamics of the system? And of course, I did a lot of C++ coding for that purpose. How is this a question? Open link? What do we have here? A lot of scientists. Very few of them are cool. I had forgotten about that clip. Anyway, so this is kind of where we're at here. So again, my old undergraduate research was doing dusty plasma physics, working with the Daemon simulation code, which admittedly is a bad name, to do molecular dynamic simulations of dusty plasma systems. That's the whole spiel. Today, I wanted to go back to the simulator, get some very basic animations done of some sort of system that I worked on at that time, right? And the reason being that when I was working on my previous video, I kind of realized I have no videos of that time in my life. And I figured, let's go ahead and grab some videos there. So I'm going to show you what I mean. If I CD into projects, scripts, there we are. I'm CD into scientific software, ls, and let me just go into Ocular scientific software, slides.pdf. Okay, you'll see here, I've got a cool visualization for warm dense matter, cool visualization for quantum systems, nothing for dusty plasmas. And again, as I said before, I do genuinely feel that if I'm going to be talking about research, I need to actually talk about research, you know? And I figure it's good to talk about undergraduate research too, even though that research isn't quite as good as the other research I've been doing. Are those numbers next? Yeah. Are those numbers next to those years? No. Those are when you cite something in a scientific paper. So let me just go ahead and Google. Of course, I don't have any. So let's just do G. I just Google myself on Google Scholar a lot. I don't know why. I do know why. I need to find my publications. So if we go to my most recent publication, which is this one, which by the way, it is now open access here. So go ahead and take a look at that if you want. This paper is now published and open access. It's not related to plasma, but I have an idea for a game. Oh, cool. What is the game? So anyway, if you go to a PDF here and you scroll down, all the citations are here. So like this guy 1 brings you down to this citation here, right? So the idea with the 1, 2, 3, all that kind of stuff was just so that I could link people to relevant articles in the description, right? So that was the point there. So the idea was that every time I have a citation or something, I put it on the board as like 1, 2, 3, 4, whatever like that, so that I can very easily link them down to the description where that information is. Ooh, by the way, that is, I don't know why there's a 1999 there. I'm sorry. What's your game idea, Trash Talk? Okay, so yeah, this guy's now open access. I'm pretty happy with it. It turned out pretty well. I'm actually very excited about this paper. I've got one more that I'm submitting soon. So again, if you guys want to talk about it, we can talk about it soon. It's a game where you play a diplomat from a European country and you're trying to stop World War I. Oh, interesting. Yeah, that is completely not related to plasma physics, but that's okay. Okay. So again, I just wanted some sort of visualization for this dusty plasma side of things. So I'm gonna CD back directory. ls here. Let's CD back one more directory. CD to daemon simulation code. Okay. I don't think they've actually made any changes, but just in case, I'm gonna do git pull origin master. And let's see if I can build this guy. It's been a while since I did the build. So the thing is, ever since I kind of stopped working on this code, very few people have been working on this code. And as much as I would like, you know, for this to become like a really cool simulator that everyone uses, the truth is it's just not there yet. The way modern research is done, and again, this goes back into the scientific computing argument I was saying before, is that if people don't care about writing good, high-quality software, they won't write good, high-quality software. And so if someone who wants to write good, clean code leaves, then it's just good, clean code won't be written anymore, you know? And that's kind of the issue, right? Like, I know when I leave here at OIST, they're gonna have trouble finding somewhere or someone to do GPUE development, because at this point it's a computer science problem, not a physics problem, you know. It's a game where you play the diplomat. The game starts with the assassination of Franz Ferdinand and goes from there. Oh, nice. That actually sounds like a really cool game. I know I don't sound like it sounds like a really cool game. I'm just really tired. But yeah, I hope it goes well. I'm actually a huge fan of the creativity of people in this community. So I'm really hoping that, like, you know, people here, I really like when people here come up with really cool stuff, you know? Okay, so we're at Daemon Simulation Code. Let's do a quick ls. I think, although I don't remember, I think I can just make this. Ha! It's building. Wow, look at that. I probably should have C-made it, but I think I already did that before. Okay, let me get some water real quick. Okay, so now we have the code building. The thing is, if I remember correctly, this code doesn't have the appropriate documentation. It's got some documentation, but not enough for me to be able to just go from nowhere to remembering how to run this. I'm gonna grab some, I'll be right back, 1 second. Ideas are cheap, the value exists in actually doing the work. Yeah, that's true. Man, ever since I've come back from the US, I've just felt really, really weak. I don't exactly know why. I've just felt weak. Like every time I go to the gym, I have not been getting anything really substantial done. I don't know. Maybe I don't feel like I'm jet lagged. It's just I just haven't been having a lot of trouble just like doing things, you know? 1 second. What do we have here? I just saw something on Discord. It's okay. I'll take a look at it later. Okay. So let's go ahead and take a look at what we have here. LS here, LS here, not LSD. Everyone says that they accidentally type in LSL instead of LS, but I always accidentally type in LSD instead of LS. I don't exactly know why. Maybe it's some sort of Freudian slip or something. Okay. So what do we have here? We should have a daemon code that I can run. So if we cd into build and then I believe bin ls here, yeah, we have the daemon here, and if I just run daemon, it should, yeah, so it's running something. I'm not exactly sure what it's running, but it is running something. Ls here. Okay, then we have a data.fits file. Good. This is about what I expected. So basically what happens is we run the code, right? And after running the code, we then have this data file that is output from the code, right? So if I run /daemon -h, it gives me kind of this help file, which tells me basically everything I need to run. Now, the thing is, if I'm being totally completely honest, I don't remember what are good parameters to run here. I know that if you're running a basic Dusty Plasma simulation, it starts with 4 particles, and then nothing really happens. But I don't really remember why that's the case. So what I'm going to try to do is create something that looks a little bit cool, and we'll see how it goes from there. So let me see if I can explain this. Basically, you run the simulation, you get the movement of 4 particles or however many particles you ask for out. And then after you get the movement of these particles out, what then happens is you get a FITS file. And a FITS file is a multi-dimensional file format. And you use that FITS file to basically do the plot, right? Okay, so let's see what I can do here. Let's see if first we can just go ahead and plot that first data file that we just got. So I'm going to do the same thing over here and cd into projects, the daemon simulation code, ls here, and I should have cd example maybe. Check.png. What is that? Check.png. Oh, okay. So that's the movement of each individual particle then. Okay. So what are all these outs that we have here? Let me see what I have here. Let's go into VI readme. Okay. This is a simple example of running daemon code. Run daemon-p params vortex.cfg. Then output the data and using a script like the one in readdata.py. Okay, fair enough. So what do I have here? I have params vortex.cfg. Okay, so I'm gonna go ahead and run this guy then. Daemon. How many particles are there in the system? However many you define. I think usually there's up to thousands of particles in a system. But I don't really remember the exact number here. So I think we're just using a small number of particles rather than a large number of particles in our system. But we could use as many as we want. Okay, so let me take a look at what we have in this params vortex.cfg. So we're going to go into params vortex.cfg. Void decay, magnetic field strength, number of particles. Oh. Okay, this seems fine. So we're actually using 100 particles here. Interesting. Okay, so let's just go ahead and run this guy, see what happens. There should be a time, a final time or something like that. Data time step, start time. Is there an end time? An end time is 10 seconds. Okay, so let's go ahead and give this guy a run. So we'll run daemon dash, I believe it's P for parameters, params vortex.cfg. Okay, we'll give it a second to run. It's running a 10-second simulation. 10-second simulation. It's currently 3 seconds done. Yeah. Okay. So, okay, it's taking some time. Oh, there must have been like a collision or something that happened there. Yeah, another collision. Well, that's cool. That means this is probably pretty cool data. And it should be outputting this to a data.fits file, if I'm correct. Let's take a look at this. Data time step. Okay, I don't have an output file, so it should just be data.fits. Now here's the thing. Data.fits, the fits file format is obviously not human readable. So what you have to do is you have to read it in some sort of weird way. So if I go into vi read data.py, basically I'm reading in a library called AstroPy, which imports the fits data file format. So the idea was that the fits file format is a multi-dimensional file format that was originally meant for astrophysics simulations, right? So here we have a fits file format reader, and I have to read in AstroPy to get this done. So let me see if I can remember how this is done. So the purpose, this file is an example that explains how to use the AstroPy package to read data from the data.fits file. Requires AstroPy. Please refer to the following website for more information. Fair enough. So first we need to get the HDU list. With Daemon, there are 3 HDUs, primary, cloud, and time step. So the idea here is that we have a multi-dimensional file format. At the start, we have primary, cloud, time step. These are 3 different kind of partitions in which we're putting data into. So we're going to output the structure of the HDU list, and now we need to grab data from the time step HDU, right? So basically what we're looking for is how the particles are moving with time. So we move to time step. This is going surprisingly smooth. What do you mean by that? Are you talking about like how I'm kind of moving forward and along with this, even though I have absolutely no idea what's going on? Yeah, I mean, this is what good documentation does for you. It's very lucky that I did this, because otherwise I would not be able to go back and remember what it was that I was doing. Okay, so basically now we need to grab the data from the time step HDU. So we set data from the HDU list data. So this means that we're grabbing data from our time step partition. And so now it says, now we have all the data for 100 particles worth of, now we have all the data for 100 particles worth of data. Okay, fine. In the following format. Data dt0 is a time, add dt time step. And then we have data 1n, data 2n, data 3n, data 4n. And this is going to be data dt, which is our time step that we're on. Then we have position of particle n, position of particle n, so xy position, xy velocity, right? So 1, 2, 3, 4, and then particle n, right? So the idea here was, let's see, what do we have here? So the x position of the second time step in the fourth particle is the following. So this means the x position is going to be here. Wait a minute. The x position of the second time step in the fourth particle. I think maybe I got this mixed up. 1 second. It seems to all just work. Yeah, that's true. I mean, I did a lot of software engineering. So when I did this project as an undergraduate, see a trash talk. When I did this project as an undergraduate, I spent most of my time just making this code usable, readable, user-friendly, all this kind of stuff. That was what I spent most of my time doing. Which is why I think my advisor was he kind of realized that I don't do so much actual research as I do software engineering, which is okay by me. I kind of like doing software engineering. Now, one thing I noticed here is that I think I'm doing something wrong, because I said the x position of the second time step for the fourth particle is the following. So fourth particle being 3 is fine, because 0, 1, 2, 3, so that's 4, right, because we start counting at 0. But this is where I think I did things wrong. I think the x position of the second time step for the fourth particle, I think these should be flipped. So it should be second time step, the x position here. Okay, so now we're writing the file. Okay, let's see what we have here. So 4p in range 4. Okay, f is equal to open out dot dat, and for I in range 100, we're going to say f dot write string data I for p in range 4 for I in range 100. Okay, so I think I got this mixed up. So that's 1 and 2, so that's going to be the x and y position. For p in range 4, this is going to be n, which is going to be the particle that we're on. But what's this I? Oh, we're writing out 100 time steps. Okay, this is correct then. So let's go ahead and change this to 100, since we have 100 particles. and I'm just going to go ahead and run that. So we're going to run Python read data.py. No module astropy. Yay-ss astropy. This is where it's going to break because I don't have astropy installed. Python 2, let's just do -s, see what happens. Dang it. Okay. I guess I'm using Python 2. Okay, maybe I'm using Python 3. So let's do Python 3 astropy. Python 3. I believe it's that. And let's see what we got. Oh, it's just Python. Not Python 3. I'm just being an idiot. Okay. Probably have to use pip. It's fine. It's how I always install things. I mean, admittedly, yeah, I could use pip. But I just always install things this way. I don't know why. It's just what I do. Just to show none. Password. Don't look. Nice. Python h5.py and HDF5 OpenMPI are in conflict. Remove HDF5 OpenMPI. I don't think I use that, so I think I'm okay. Oh. Oh. Well, that sucks. Unable to satisfy dependency HDF5 required by Python h5.py. Removing HDF5 OpenMPI. Okay. Let's see what we have here. Could not install package due to environment, permission denied. Do I have to use sudo for pip? I was not aware of that. Okay, fine. It seems like it's installed. So let's go ahead and run Python, not version, Python read data.py. Okay, now we're ready to file. Cool. If I do an ls here, that means we have all this data to look at. Wow, amazing. Great job, guys. Fist bump. Okay, so we have the data available. So now we'll see what all the particles are doing for all 100 particles, and we'll see what we have here. So I should have a GNU plot. I do not. Darn. I do not have a plot.gp, so I'm going to go ahead and create that. It might be a bit confusing, but I think it should be okay. So if I want to plot all of these guys, am I sure I don't have a GP file? I was pretty sure I had a GP file. Well, let's just go ahead and go into GNU plot real quick. So let's do GNU plot, and I'm just gonna plot. Out 0, 0.dat with lines and see what happens. Okay, so this is the movement of the first particle. Should be fine. So if I replot, I'm just gonna replot a couple just to make sure this is okay. So replot out. Let's do 99. Yeah, okay. So you can see that these two particles, we had one that I think started from here and moved out like that, and another one that started from here and moved out like that. This is honestly kind of what we would expect. So now we have 100 particles. They're all starting like somewhere here, and I just want to plot all of them. That's what I'm going to do next. Okay, looks good. And what I'm going to do in the end is I want to draw like an animation. So I'm going to want to animate the movement of all of these particles and stuff like that. We'll see how far we get today. So I guess what I'm going to do is plot for... Ooh, hello there. Yeah, I guess I'll do plot for... Oh, you know what I could have done? Let me change the way that we're Let's change the way that we're doing this. Let's do Control D, and let's go into... let's remove all the DAT files. Remove start.dat. Okay, let's go into vi read data.py. And actually what I'm going to do here is I'm going to output each time step separately. So this means that every single time step we have the entire cloud available to plot, rather than doing the way I had been doing, which was having it so each particle has all of its time information in each script. Does that make sense? So this should make it a little bit easier to parse. So we're going to open data PW, but I want this to be I. And now down here what we're going to do for I in range 100, f.write string data tab new line. Okay, so then I think what I'm going to do is I'm going to mix up the I and the P here. So let's do P and then the I here. And this should, if I'm doing this correctly, let's just see what happens. So we're going to run Python read data.py. I is not defined. What do you mean I is not defined? For I in range 100. Oh. Yeah, okay, I see. So for P range, this should still be P. Yeah, should be okay. Python read data. No writing to file, ls here. And let's just run GNU plot. And we're just going to plot out 0 dot dat and see what happens. Okay, there's all of our particles in the first time step. That seems fine. So now let's do point type or something like that. So we're going to do, let me do test real quick. What do we want? We probably want this circle, so we're going to do point type 7. So PT7. Oh, that wasn't what I expected. Let's try here. Oh, come on! How do you change the point type? I think maybe I don't have this guy. There we go. So now there are all these little purple circles. And let's just plot some more stuff over here. Again, guys, if you have questions, comments, concerns, anything like that, the chat's a bit quiet today. I do understand. Okay, so if you have questions, let me know. Okay, cool. So that means all the particles start out here, right? And then they finish up here in this weird, like, clump, right? So we can see a transition, probably, if we plot them from, you know, starting out here and then moving into this clump. So I guess what I'm going to do is I'm going to create a quick script that allows for me to start from this weird spaced position and then kind of come into this cloud thing, you know? So let's see what we can do here. I'm going to have a for loop. So I guess what this is going to look like in GNU plot. Let me just go ahead and try this out. Let's go into vi plot.gp. I guess it's going to be do for, I always forget for loop syntax in GNU plot. Let me just go ahead and look here. GNU plot for loop. I'm sorry, I know I should have this understood or remember by now. So plot for I equals 1 to 1,000. Data to I using file. Okay, so what I want to do is multi-line, something like this. By the way, I've been not paying attention to my notifications, so if someone followed or something, I apologize. I've got the notifications up now, so I can look at it now. Okay, looping multiplot and do for, yes, that's what I'm looking for. So what I'm going to do is do for I equals 0 to n, where n is 100. I'm going to open this up, and let's go ahead and go up here. So we're going to set terminal PNG Cairo. Okay, set size square. All right, and down here we're going to say set output, and I guess the output is going to be some sort of string. So I think we're going to have to do sprintf. Sprintf. I'm sorry, I need to output it so that each image file, each image file is a different name. Does that make sense? Let's do sprintf. Cube FFF. Add cube. Okay, yeah, this is what I'm looking for then. So I guess what I'm going to do is, interesting. Sprintf. I guess it's going to be the following, and forgive me if this isn't right. So I'm just going to have an output as, oh, but I also want to do, didn't I already do this before? Let me go and open up a new terminal, and let's see if we can find where I did this before. So cd into projects, ls, I probably did this during the Christmas tree visualization. No, I didn't do it during the Christmas tree. Where would I have done this before? I guess cd into Simuleos. Simuleos, ls here. What I'm trying to do is output a bunch of image files that will then turn into a GIF. Right? So the question is, I probably did this in Christmas tree, wherever that one is. Tree traversal tests. That's probably in Fractal. What do we have here? Data fractal2.jpg, fractal.png, fractal.tiff. Tree images. Where is it? Tree images. Okay, let's do Mirage 000.png. Okay, here's our Christmas tree visualization. That's what I wanted to see. Nice. So now if I just kind of pull off of this. Oh man, this is back when... every time I look back at this type of stuff, I'm always kind of amazed that we did this. That was kind of nice. I still haven't made the ThinkerCon video. Oh, I'm so far behind on everything. Man, so far behind. Anyway, let's just go ahead and keep working on this. So, CD backup directory, and I should have a GNU plot script here. Remember those trees? They were super fun. I don't know, like, man, I was never able to make a video on it. Let's go to plot.gp, plot.gp. For I equals 0 to 138, set output, that's what I'm looking for there. sprintf, images, so I guess I'm gonna do the same thing here, images, something like this, and then yeah, this should work. Let's go. Images, but it's not gonna be fractal zoom. It's just gonna be, what are we even doing here? I guess, plasma, 05d.png, something like that. And then we're gonna plot that guy. So it should be plot, and we use the same command we just did. So it's gonna be plot, and it's gonna be sprintf of, it should be in the file that we're in right now. So it's gonna be sprintf of out, and then it's gonna be, I believe, this dot dat, where this is going to be I, and then it's going to be point type 7, and then we should just print I. Okay, let's go ahead and right quit this guy, make directory images, and let's try running that. GNU plot, plot.gp. Okay, vi plot.gp seems to be doing something, which is nice. Let's do 299. Okay, let's cd into images, ls, and let's do a quick mirage, plasma.png. Ho ho, my friends, look at that. It's doing something weird. I don't know why it's doing this weird shimmery thing, but it is doing something. Okay, so let's see if we can figure out what's going on with that shimmering thing. So here we have all the particles starting here. They go down and down and down and down, and then it goes back up. Where does it go back up at? At 40. Huh. Oh, the scale is changing. That explains it. Yeah, the scale's changing, right? I got it. Yeah, I don't know why the sprintf is there. I guess if I change the background to black, it wouldn't be there. I don't know how to get rid of that, honestly. Okay, I get it. I understand why it's doing that thing. So let's go ahead and make sure the scale is consistent. So let's pop up here, and we're just going to say the x and y range are going to be from negative 0.015 to positive 0.015. Let's go here and let's go into vi plot.gp. Oh, I'm back at directory. Plot.gp. Yeah, let's do it. Oh, vi plot.gp, and in here we're just going to say set x range, sorry about that, from negative 0.015, negative 0.015 to positive 0.015, and we're going to do the same for the y range here. Okay, set size square, set view map, set palette model. Let's actually set the same palette model, see what happens. I'm not really sure what's going to happen, but I'm just gonna go with it. So now let's run the last GNU plot. Okay, and now we're just gonna run mirage images plasma 0000.png. Okay, that did nothing, but fine. Cool. Look at that. That's what we expect. That's super nice. Okay, so what we see here is all of these particles starting way out in the distance. And here's what's going on. All of these particles have a negative charge that is associated with them, right? So they are all repelling from each other. However, the plasma itself has a very strong electric field that is pulling all of the particles in, right? Because the plasma in general is basically very highly, there's a very large amount of electric charge at the center of the plasma, right? So all the particles are coming in, and they're basically being attracted to each other. But then as they get really close, they actually start to repel each other because they're they're negatively charged, right? So they're coming together because of the plasma, and then they get really close, and then they fly away because the dusty particles are all of the same charge, right? So that's kind of what we're seeing here. Because the plasma has a high positive net charge that loss of electrons, right? Yeah, it's probably something like that. This feels like that time I tried to work electrostatic particle containment. Oh, yeah, tell me more about that. That seems really cool. Anyway, I'm happy to say that this is working the way I expect. So what I'm going to do now is I'm going to run this simulation for a bit longer. So let me go into VI, what is it, params, vortex.cfg. I don't know why I called it params of vortex, honestly. It's probably just because I had vortices on my mind from the superfluid stuff I was doing before. And let's change the end time to, we could do 10 times as long, but I feel like that's going to be too long for this simulation here. So let's just do 5 times as long. Okay? Now what I'm going to do, ls here, I'm going to go ahead and change to a directory, which is going to be a data directory. So let's go ahead and make directory data. I don't know if I have the ability to set an output data directory with daemon, so I'm going to go ahead and cp what we have back a directory, so params vortex.cfg here, and I'm just going to run daemon dash p this guy here. Okay, give it a second. It's going to take a bit of time, so we have time to talk while that's happening. I want to run htop right now just to see how it's utilizing my cores. Ho ho, my friends. That's okay. Parallelization. Well, okay, it's using all my cores, but I think it's playing nice, so I think I'm okay. Let me go ahead and quit here, and I'm going to cd back a directory. Actually, no, I'm going to go back to my previous terminal that I had up over here, and I'm just going to do cd back into example, ls here, and I'm going to remove all of the star.dat files. Now I'm going to go into vi plot.jp, and I'm going to add a data directory to this guy. So it's going to be data here. Okay, nice. So we're going to just let these guys go for a bit, and then we're going to plot it at the end. Now, admittedly, there's some weird things going on with this plotting script. I again don't remember why it's forcing the sprintf or whatever to appear, but we'll figure that out in just a second. So we'll keep working on the plotting script in a second once we have this simulation done. Let me go ahead and get some water. Basically, I was working on an electrostatic with some dynamism, but mostly static lens for basically a do-it-yourself CRT display, and was plotting field equations resulting from charged particles on Rails with Python. Oh, that's quite cool, man. Like, good job. I'm a fan. Of course, I'm a fan of all that kind of stuff. By the way, I recently asked Twitch, and of course they're not going to do this, but I did recently send a submission to Twitch for a new tag. You know how we have like the programming tag and all that kind of stuff here. So we have programming, software development, educational writing. I asked them to create a new tag for research particularly. I don't think this is going to happen, but it is something that I would like to have. Because a lot of the stuff I'm doing now is research. It's not really educational. It's more research, you know? And I do feel like I'd love to have more of that type of stuff done here on Twitch. So I'm going to cd back a directory. So we'll see what they say. They're probably going to say no, and that's fine. So let's run GNU plot, and we're just going to do plot.gp. Cannot find data out 0.dat. ls data here. Oh, that's because it's in a FITS file. I have to get it out of the FITS file. How do I do that again? There's like a Python read data. So let's go to vi python read data.py. And what do we have here? Open out.dat. So this is going to be not out.dat. It's going to be, where is it? Data.fits. It should be data and then data.fits. Data/data.fits. And we're going to output it here to data.fits. And this is now going to be 500 instead of 100. Okay. So now we're going to run python read data.py. It'll take a second, I believe. I don't really know how long. Can you ask them to add LaTeX typesetting to Twitch chat too? Oh, I'm sure they would do that. And now let's see, we should have all the DAT files. So let's go into VI GNU plot here, which should now be to 499. Okay, and let's go ahead and give this guy a go. So it should be plot.gp, and let's see what happens. It's partially to try to understand electrostatic lens principles better, but also I was trying to determine what properties could be guaranteed by the system. So, for example, some particle accelerators only release on first approximation particles at a certain speed because of their design. This sounds like a pretty good idea. I'm kind of surprised there isn't already a research tag. To be fair, I mean, this is why I started the discussion on this particular video about research to begin with. People just don't do research on Twitch and YouTube. They just don't. There's some channels, like for example, 2-Minute Physics on YouTube that does a lot of research, and there's a few people here and there that do research on Twitch, but for the most part, it's not something that people do. And it's something I really want more people to start doing. You know what I mean? It's just not being done. And so that's why I'm not switching gears, but I'm incorporating the research I'm doing into my YouTube channel. And again, why I'm doing this video to begin with. So let's go ahead and do Mirage, images, and we're gonna go into plasma 000.png. Okay, let's see what happens. So we scroll down, all the particles kind of move together. I'm just gonna scroll down like this. They fly apart, and I imagine they're not gonna come back. Oh, are they? Look at that breathing mode. Wow, look at that. Ho ho, that's beautiful. Look at that. Ha, and they say I don't know plasma physics. They're correct, I don't. I have no idea what I'm doing. Okay, Breakless Jumper, thank you so much for following. Let's see. It's mostly cooked by recipe type stuff. Still has value, but I'm a research type, not, or at least it's a redneck engineering type. Dude, the way I see it, like I said this before on a previous video, but like, you know, you see all these people making fun of flat earthers and stuff like that, but honestly, a lot of the experiments that they're doing, they're kind of real science, you know? And so even if you think that the research you're doing isn't real research, you know what I mean? Like, even if there isn't a publication coming out of it, the very fact that you're following like the scientific process and you're enjoying the prospect of just learning in that way, I think that's what you should be doing. And I would love to, I'm very appreciative, and I feel like more people should be doing that. I just feel like we kind of pretend that science is this club where, you know, if you're not part of the club, you can't really do research, but that's not true. Sure, it might be hard to publish, but you can still do research. Does that make sense? I don't know. I mean, I'm not saying that you're not doing like real publishable research. I'm just saying that a lot of people are afraid to do it because they're not scientists, quote unquote. Yeah, so this is really cool. Let me see if we can describe what's happening. So there are basically two forces here at play. There is the repulsion of each of the particles from each other, right? So like I said before, each of these dots are these globs of charge, like 1,000 electrons in charge, right? And they're all repelling each other, right? The thing is, when we initially put them on the grid, they have a certain spacing that allows for them to just kind of move around freely. What ends up happening, though, is they're all attracted to the center of the plasma because the plasma itself has just a very high force of attraction towards the center. So they all come into the center, you know, something like this. And as they're all coming into the center, here, they hit each other, right? So they hit each other and start to fly away. And this is because there is a very strong level of electrostatic repulsion between the particles at this point. So here they're starting to fly away. And then at this point, you know, they reach their maximum distance away from the center of the plasma. They're kind of breathing out. And then they come back in because, again, the plasma is pulling them back in. So they just go back and forth and back and forth. And admittedly, there's some really cool stuff we can do with this. But for now, you know, so for example, if we add in a bit of a drag force in the plasma itself, these particles will be losing energy as they kind of move in and move in and out, in and out, and in and out, right? And as they're losing energy, they slowly but surely start to collect into their lowest energy state, right? Because they're always losing energy. And as they go into their lowest energy state, what is kind of crazy here is they form a closest packing type of solution. So you create that same type of triangular vortex lattice, or that triangular lattice that you would expect from, for example, vortices in superfluids, or vortices in type 2 superconductors, which is actually why a lot of people have recommended using a system like this to study that type of vortex dynamic, those types of vortex dynamics. It's called the point vortex model, or the vortex filament model, where people assume that the vortices are just charged particles, and then they move the vortex dynamics in a superfluid basically acts like a charged particle, right? Obviously not like these charged particles because there's a plasma underneath, but just normal charged particles. Is there a point when the particles have zero velocity? Do they retain some momentum, or is it purely electric charge causing the repulsion. If they're not moving at all, then it's just purely the electric charge causing the repulsion, I guess. But basically that's what I was saying before. They form this closest packing type of triangular structure. By the way, Sir Waffle Gaming, thank you so much for following. Really appreciate it. Okay, cool. So let's see if we can buff up this plot a bit, because I don't like the fact that it says Sprint F here. So what I'm gonna do is I'm just gonna say no title, and I'm gonna see if I can plot on black, just because I like black backgrounds. So we're gonna do plot here, and we're just gonna do, ooh, hello there. 7, and then I think I can just do no title, and that should remove the title. Right, that. Let's see what happens if we run GNU plot, and then we run the last Mirage. Give it a second. I probably shouldn't have plotted all these guys. Ho ho, there's the Sprint F. It's gone. So now let's go ahead and see if we can plot on a black background. So let's see what I'm going to do here. I'm going to go to GNU plot, inverting colors. Inverting colors. Okay. How to reverse hot color palette. What I want to, no, that's not what I want to do. I want to, black background, GNU plot. Okay. Background color. Convert the PNG. Fill black opaque. Set terminal PNG. Okay. So it says set key text color, set title, set object, set fill solid color. Oh, I see what they're doing. They're putting a black box in the background. Let me see what I did with the Christmas tree visualization, actually. Set palette. I was pretty sure. Oh, this is fractal zoom. Ha. Okay, let me see what else do we have here. There should be like a fractal zoom plot, Barnsley tree.dat, lsstar.gp, cscan plot barnsley.gp. Let's plot Barnsley tree. It's going to vi plot Barnsley tree.gp. Yeah, that's what I'm looking for right here. Nice. So let's go ahead and grab this guy, and I'm going to go into nope, where is it? Should be vi plot.gp, and I'm just going to put a black object in the background here. Ed there, write that, quit, and let's just see what happens if we run GNU plot.gp and see what it looks like. Cool. So we're getting there, guys. Like, we have a visualization that I'm happy enough to put into the video. So let's run the last Mirage over here. And it is, there we are, look at that. It's pretty cool. Not gonna lie, it is pretty cool. Yeah, okay, I'm a fan. I am a fan of this. Admittedly, I kind of wish that the we could still see the plot around it, but that's okay. We'll get there. So let's see if I can change the color here. So let's see, text set key text borderline color. Oh, okay, yeah, that's fine. Let's do something like this then. Via plot.gp, and I'm just gonna post it up here, see what happens. Right, quit, and then we're gonna do GNU plot and run the last Mirage afterwards. And again, guys, if you have questions, comments, concerns, feel free to let me know. I apologize, today's going to be a short video. There we go, look at that. Ho ho! It's yellow. I guess it probably looked better as white. Let's go and change the particle color while we're at it. Let's see, point type. I think if I just do GNU plot test, it'll tell me how to do this. GNU plot, and let's run test. Okay. Let's see, can I change the color? Probably can. Okay, let's just do Control D here. Let's do Mirage Images. No, I'm gonna do plot.gp. I'm gonna change this to white. And let's just, what color should we make the points? I guess we'll make them white too. Plot.gp. How's the plotting chapter? It's coming along. I'm mostly there. I mean, I worked on it a lot. Changing point color. Yeah, I mostly have it done. I need to get the plots in there. I spent a lot of time on the plane working on it. RGB is just RGB. Should have known that. RGB. Here. In fact, a lot of the stuff that I've been Googling is in the plotting chapter. Unexpected recognized token. What? No title LC. Oh, do I have to have an LC in there? Oh. Yeah, so basically all the stuff I've been Googling is in that chapter. I don't have it up. I'm curious if numerical stability affects anything you're doing here. I've been trying to master the effects of things like floating point number behavior on my calculations. For this particular simulation, we don't usually run into any problems. So the numerical instabilities usually come from having a time step that is too large, which you'll run into situations like that here, but usually we run with a sufficiently small time step so that you don't see those problems. Also spatial steps too. If you run with a spatial step that is too big, you'll also run into a similar problem. Come on. Point type 6, point style 2, no title, LC RGB blue. The LC is ignoring labels. Let's see. Oh, okay, so let's add no title to the end there. Maybe that's my issue. Okay, that worked. I don't know what you mean. Wait, what do you mean cross-platform determinism? Let's see. So let's go into Mirage. Should be here somewhere. Here? Okay, so here's all of our particles. Nice. So they're all coming in, and then they're all going to come back out. Okay, cool. Cool. Nice. Okay, I'm a big fan of this. I'm surprised we actually got so much done. I'm not going to lie. I was expecting this to be like kind of a flat-out failure. But no, we've got a basic simulation that I could very easily put into my video. So yeah, I'm pretty happy with that. Sure, I'm gonna have to use FFmpeg to turn it into an actual video, but you know, I'm pretty happy with this so far. I think it looks quite nice. Yeah. Okay. Nice. Let me see. What do we have here? It technically has. Wait. It technically has to affect it a tiny bit. Wait, what are we talking about? What has to affect what a tiny bit? Sorry about that. So this ought to be pretty simple, but a lot of things that should be simple aren't. So I guess I'm curious. Yeah. I'm sorry, I don't understand either of these two comments. Could you guys elaborate? I apologize that I'm not able to quite follow that conversation. Let me go ahead and get some water real quick. Okay, so anyway, we got this Dusty Plasma simulation working in like 30 minutes. That's not bad. Blueberry King, what up? How's it going? Thank goodness that question was recognized. Otherwise, I might have missed it. I'm doing well. How about you? We're about to actually to wrap up today's stream. We have about 5 more minutes. So if there's anybody that you want to raid at the end of stream, feel free to let me know, and we'll totally raid them at the end. Floating point number accuracy has to affect the simulation a tiny negligible amount, right? Yeah, the thing is, it is pretty negligible in most cases. Doing pretty well myself. Thanks for asking. Oh, cool. I'm glad you're doing well. Let's see. Okay. Every time question bot. Hey, he just wants to welcome people to the stream. Cool. So I guess I want to finish this particular stream with a bit more of the discussion on the research before. The thing is, I don't know how to put this, but I know that research isn't... I don't know how to put this. Someone told me once that research is not sexy. That's what they said. They said that if you're going to do research in a public space, like, no one's gonna watch because no one cares, you know? And I just feel like I want to challenge that notion, you know? I just feel like, I don't know, I feel like, to me, watching people do research, watching people do programming, this type of stuff, I find it really cool and interesting. It's something I want more people to do. Cross-platform determinism, to me, means it gives the same results no matter which platform or tool set. If various CPU models can't round in a different way, if using a different OS doesn't mean the math libraries are subtly different, if no compilers were able to apply math rule. Yeah, I don't usually run into those issues, but that's because I specifically write code for Linux. You can run it in a Mac usually, but I don't write code for Windows at all. And usually on Linux, basically, you just modify your CMake file to make sure that everyone has the right dependencies and libraries, and you're fine. So there isn't usually an issue here. I flat out do not support Windows, period. It's just a pain in the butt to do, and it's not really worth doing in my case, because most of the people who are going to be running code will be running it on Linux. because they're going to be running it on an HPC or something like that anyway. So I have to support Linux, but I don't have to support Unix in general. So I don't have to support Mac, and I also don't have to support Windows. So it's kind of, I just cut it out. Kills me how monkey see, monkey do. It's like the glass ceiling of creative endeavors. I don't know what you mean by that. But yeah, so as far as this research discussion about whether it's interesting to watch research or not, I'm not really sure I have an answer to that. I do know that in general, my research streams are not super popular, but they could be, and I don't really exactly know how to make them more popular. Because to me, like, they're super interesting and fun and enjoyable, but I guess, you know, I'm not the one watching them, you know? And for me in particular, I know I have trouble, especially because I do it at 5 in the morning, I get tired. So I don't know, I'd just like to talk a bit more about, like, what you guys think about what makes a good research stream, you know? Anyway, that's it for today, guys. I think I'm gonna go ahead and close for now. I don't see anyone that we normally raid, so I'm not really sure what we want to do there. We could do Dowright, I think. I remember liking his stuff. So let's go ahead and do him. Good on you. Alas, I want to reach a random people on various platforms. I def for Linux first, but I'm keeping my eye on details for keeping it consistent. Yeah, the thing is, I just don't need that. Now, the question is whether I'll be back or not in a few hours. So normally, guys, I would be doing an additional GPUE stream at 9 o'clock a.m. Or rather, I want to start doing these streams again. I missed them for the past week or two. I will try to be back at 9. I'm not going to give you any confident answer of whether I will or will not be back, but I will try to be back at 9 and just do some GPUE development there. So if you want to do GPU computing and superfluids, feel free to come then. No, it's 9 o'clock a.m. Japanese Standard Time. I don't know what time that is anywhere else, so it's 9 a.m. That's when it is, not 9 p.m. Jamie Pine? Yeah, we could do Jamie Pine. So anyway, I will try to be back then. May or may not be back. So if you're new here and you want to hang out, feel free to go to Discord, where I'll let you guys know more about the stream there in the stream chat. For now, I think I'm gonna go ahead and close shop. So thanks guys for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. I may or may not be back in a few hours. Just feel free to go to Discord and we can talk more there. And that is it for the day. I'm happy that we actually got this simulation done. I can now go ahead and start working on my next video, which will be the first video in a series talking about research that I've been doing recently. So I'm pretty excited to see where that goes. It's going to be a bit of a lame video. The first video is going to be a bit slow, but the other videos should be pretty good. D&D Wanted, thank you so much for following. Really appreciate it. Okay, and that's it. I will see you guys around next time. Let's go ahead and raid Jamie Pine live. Jamie Pine live. Cool. Go ahead and get that guy started, and I'm gonna go ahead and head out. See you guys. Have a wonderful time.